A 99% of Earth's history is totally invisible to us. The 4.5 billion years is almost incomprehensible. And to map this, scientists created the Geologic Time Scale. It is a chronological framework defining Earth's history. This scale is organized hierarchically uns, eras, periods, and epochs. The largest division is the un, spanning billions of years. The first un, the Hadean, was a fiery, chaotic beginning. And now that we understand uns, let's explore the next level eras. The eras mark major shifts in global chemistry or life. The Great Oxidation Event dramatically redefined the planet's atmosphere. And these boundaries often reflect profound extinction events below. The Paleozoic era ushered in the explosion of complex life forms. Within eras are periods, our most commonly cited time segments. Periods are defined by specific, recognizable fossil assemblages. But each period introduces new dominant biological communities. The Mesozoic era, dominated by the reign of reptiles. Consider the Jurassic period, the peak of their massive diversification. But every period ends, often abruptly, through geological catastrophe. The signature iridium layer marks this boundary event clearly. But the Cenozoic era, the age of mammals, followed this reset. Mammals rapidly filled vacated ecological niches across the globe. The smallest formal division used in this system is the epoch. Epochs often represent significant regional climatic fluctuations. Our own species' history fits entirely within the final moments. If Earth's age were one single year, humanity arrives in the last minute. The Pleistocene epoch defined the repeated advance and retreat of glaciers. We currently exist in the Holocene epoch, the stable warmth post-ice. How do we anchor these divisions? Through radiometric dating. The zircons, containing trapped uranium, act as tiny geological clocks. But now that we understand the dating methods, let's review the major eras. The Precambrian covers nearly 90% of Earth's entire existence. Life remained microscopic, single-celled entities for billions of years. The Cambrian explosion marks the abrupt start of visible complexity. The Ordovician saw diversification of early marine invertebrates explode. Life bravely began colonizing the barren, rocky surfaces of the land. The Devonian period is nicknamed the Age of Fishes for good reason. Early four-limbed vertebrates experimented with shallow water exits. The Permian period concluded the Paleozoic era with land unification. But this boundary holds the largest known mass extinction event recorded. Life slowly recovered, paving the way for the dinosaurian lineage. The Jurassic period brought specialization and tremendous size increases. Predation and defense mechanisms evolved to match this scale. Crucially, flowering plants began their integration during the Cretaceous. On the Cenozoic era, starting 66 million years ago, is our time. Mammals diversified rapidly, filling almost every available niche structure. Grasslands expanded globally during the Miocene epoch specifically. This favored specialized herbivores adapted to abrasive grasses. The Pliocene and Pleistocene saw key evolutionary experiments unfold. Tectonic shifts continually modulate global climate patterns over time. Submerged deposits and mountain building obscure vast chunks of history. The law of superposition remains our fundamental tool for sequencing. Unconformities represent significant, unrecorded gaps in the Earth record. These boundaries are the critical markers that define the era transitions. Sea level fluctuations drastically redraw continental maps rapidly. Some life forms persist through multiple periods, showing incredible resilience. But biological evolution is inseparable from planetary geochemistry. The sheer scale reminds us that geological time moves very slowly. Yet, modern human impact is rapidly defining the next epoch. We are stewards of a deep, continuous story written in stone. Mastering the scale grants us essential context for our fleeting moment.